Okay, so this is the very start of a pretty big topic where we're doing antiderivatives, and then later we get to talk about what integrals actually mean or what you can do with them. Some of it will get a little introduced, but just to start with, the way it sounds, antiderivative, is that you're doing the opposite of a derivative. And so if we take some that we already know, some maybe not too difficult derivatives, and say we have a function, and we want to know what's the derivative of that function. So let's say we do like x squared, 4x, we'll take some simple ones, 1 over x squared, and sine of x. All right, so now we want derivatives. They're all single terms. I can make them longer if I want to. In fact, maybe just for one of these, I'll add a, let's make this 1x squared plus 5. All right, so what's the derivative of x squared is 2x, and what's the derivative of 5 is a constant, so it's 0. What's the derivative of 4x to the first? Multiply the, probably at this point you don't even think of it as power rule, but it technically is. Multiply the one exponent down, and then when you go x to the 0, you don't have any x's, so that's why you're just left with 4. All right, 1 over x squared, probably a good idea. If I write it as x to the negative 2 first, makes it a little easier to see. So that's negative 2x to the negative 3. Right, power rule, I subtract 1 off, and maybe it would look better if I wrote it like this. And then the derivative of sine is cosine. All right, what we're going to do in antiderivatives is say that we didn't know the original function. It's literally like it sounds. We're going in the opposite direction. And so if somebody gave you the derivative and said, hey, what did the original function look like? You could go back in the other direction and say, what I take the derivative of to get 2x. And eventually you might notice a pattern, and then we'll write that down as a more concrete kind of formula. But 2x, so I must have taken the derivative of x squared, right? And sometimes you can take that all as 1, or sometimes you can look at, well, when I take the derivative, I make the exponent 1 less. So if I go the other way, the exponent's got to be 1 more, and this one just coincidentally, that front number works out perfectly, right? The derivative of x squared is 2x, so the antiderivative of 2x is x squared. Another thing that we might as well talk about now is, remember how that one was x squared plus 5? And so there's no way I can just pull that constant. I can't know like psychically what number may have been there. And so you'll see a lot of these indefinite integrals, they have a plus c on them. What it means is there could have been a constant there, right? Earlier when we did it, there was a plus 5. There could be a constant there that got canceled out when I took the derivative, but there's no great way for me to know what that was beforehand. And so on all of them to compensate, I know there could have been a constant. And so before I started, I just put, the derivative of the antiderivative of 2x is x squared. If I was going the other way and taking the derivative, there might be a constant there. Unless they give us more information, like a point, we'll do some like this where they have an initial starting point. You can't often find out what that is, but there could have been a number at the end of it that would go away when we take the derivative. So that's why all these indefinite integrals have a plus c on them. And then same thing, sometimes it helps to think about raising this by 1 power, so there's no x there. But before we went, right, if it was x to the 0, it's because this started out being 4x or 4x to the first. Right, we don't have to write the to the first. All right, then the same way as when we do derivatives, it's a good idea to rewrite these. If you just try to look at what was the antiderivative of this, it might be hard to remember that you actually have a negative number there. So it's significantly easier to look at this and say, okay, I subtract 1 off exponents. So notice my exponents are getting 1 bigger when I do antiderivatives. So same thing, if I need this exponent to be 1 bigger, that's actually negative 2. And then I can think about, do I need a front number here? So if I take the derivative of this, I get negative 2x to the negative 3. So it seems to work out the way it is. I don't have to compensate anything. And then if I want to rewrite it, I can. So way easier to see the relationship between this and this than to go all the way from fraction to fraction. And then these ones you have to be really careful with, especially because you get really used to derivatives, and now we're going in the other direction. So all the time you kind of stop and you're like, wait, I'm taking the antiderivative. I'd say sine and cosine cause that to happen a lot because we're thinking, what did we take the derivative of to get an answer of cosine? So you have to think, okay, the derivative of sine is cosine. Sometimes people will start thinking derivatives again and want to say derivative of cosine is negative sine. So we have to back ourselves up one. We're going, what did we take the derivative of to get an answer of cosine? Okay, so if we start noticing some stuff about these for antiderivatives, if in a derivative you take the exponent and subtract 1 off it, notice in all these cases, if we were going in the opposite direction, we end up adding 1 to the exponent. And we just had some where the derivatives worked out really nicely. So let's try to write down one that maybe doesn't work as perfectly. Say if we want the indefinite integral, so antiderivative, and here's our notation for this. So if we want the antiderivative of x to the 5th dx. So first thing I'm going to think is, okay, if I was doing the derivative, I subtract 1 off the exponent. So for antiderivatives, I want to add 1 to the exponent. So I know instead of x to the 5th, I'm going to have x to the 6th. But then you notice, if I just took the derivative, right, does this get me back where I started? The derivative of x to the 6th is 6x to the 5th. And so you're like, I don't want that 6 there. What can I do to compensate for it? And so some of them work out really nicely, right, where the 6 was already in the answer. And so what you want to do is, if we divide by our new exponent, then it won't show up when we take the derivative. And then also remind ourselves there could always be a constant there. I'd say in the beginning, because we're way more used to derivatives than antiderivatives, just check everything in your head by taking the derivative. So think, what is the derivative of this whole thing? Right? What is d dx of this? And so go 6x to the 5th over 6. Notice how that cancels out. So you're just left with x to the 5th. So you're like, it does actually work. Even if you don't explicitly write your check, that's what I would be thinking in my head when I'm doing these all the time, because we're way more used to derivatives than antiderivatives at this point. All right, then one other, so if we want to write down kind of a formal rule for this now that we think we've picked up some kind of pattern, the opposite of power rule, right, instead of subtracting 1 and multiplying by your exponent, or multiplying by your exponent and then subtracting 1 from your exponent, we're going to do the opposite. We're going to add 1 to our exponent and divide by our new exponent. And so for anything to a power, right, x to the 10th would be x to the 11th over 11. X to the 3rd would be x to the 4th over 4 plus c on all of them. And so there's the opposite of power rule for antiderivatives. That might also run you into one other interesting one that you have to kind of remember, but I'd say here's how I remember it, because I try this rule first and then it doesn't work, is what if we're trying to take the antiderivative of just 1 over x, right? So x to the negative 1 dx. So you notice real quick, if you try to use the power rule, see how since we add 1 to our exponents, you end up with x to the 0 over 0, and then you're like, wait a second, that can't happen. So if you remember, we had one kind of oddball one where when you took the derivative, the answer would give you 1 over x, and it was the natural log. And so this is just the oddball one out, but usually, I mean, this is how I remember it, is I kind of try it first because you get in the zone, you're doing a lot of them in a row, and all of a sudden you're like, wait, my power rule doesn't work on that one. Is because the antiderivative of x to the negative 1 or 1 over x is natural log. And then they put an absolute value because technically when you're going in the opposite direction, it would have to be, you can only put positive numbers in log, so assuming to make the domain work out correctly. But picture, remember that in our derivatives was kind of an odd man out. The derivative of natural log is 1 over x. So same way, the antiderivative of 1 over x is natural log. So that's kind of the oddball one that when you see exponents, you have to kind of remember, or you can try it the other way and it will remind you because you're like, wait a second, that didn't work out. All right, let's find a good one from the homework. And I'll leave our rule down here for just a second. let's say we have the indefinite integral where they're asking for the antiderivative of x to the fourth plus quantity, right, times x minus 3. So x plus 4 times the quantity x minus 3. All right, so first thing is, you only at this point, and really actually going forward other than use substitution, good news, bad news, there's no opposite of product rule, opposite of quotient rule. It's not that if you had something perfectly in the version of product rule, you couldn't reverse it out the answer, but there's so rarely do they work out that way that we don't have a general way to do those. So if you see something like this, that's a clue to you that I probably just want to FOIL it out, because I can use this rule that I have written down, right, my power rule for antiderivatives. I can use it on individual terms, and I could really quickly turn this into individual terms by saying it's x squared plus 4x minus 3x is plus 1x. So x squared plus x minus 12. And now I can just do each term individually using this rule. All right, so the antiderivative of x squared, we want to add 1 to the exponent. So x to the third over 3. And so picture if you took that derivative, you'd get 3x squared, and the 3's would cancel, so you'd just be left with x squared. So you're like checking, if I take the derivative, do I end up back where I started? And then 1x to the first, so my new exponent's going to be squared. Then I need my over 2, so if I take the derivative, I get 2x, the 2's cancel out. And then minus 12, there's no x there, so I must have taken the derivative of 12x to get there. And then there could be a constant hanging out at the end, because picture when I take the derivative, that would disappear anyways. So if I take the derivative of this, I end up back here as my check to make sure that worked for the antiderivative. So they're exactly like everything you know about derivatives, except we're going backwards. It also works in the context of a lot of real life problems. So notice we had a bunch of things to remind us that the derivative gives us the rate of change. And so we also had that relationship that if we had a function that told us the position, if we took the derivative, we'd get the speed or the velocity. Right, so if I have a function over time that tells me where something is, and I take the derivative, I then get the rate of change of where it is, so how fast it's moving, so velocity. And if I took the derivative of that, I'd end up with acceleration, the rate of change of your velocity, so how fast is your speed changing is acceleration, or deceleration if you're slowing down. All right, now that we have antiderivatives, right, derivatives take us in this direction. Now that we have antiderivatives, we can go backwards up the chain. If we knew acceleration, we could figure out velocity, and if we knew velocity, we could figure out position, or you could just keep going. So there'll be questions where they give you one of these, and they want you to go back up the chain. So here's one that says an object with an initial velocity of 45 meters per second. So initial velocity, 45 meters per second. At the end, I'll show you why they said that. And then they say its acceleration is given by the function a of t equals negative 6t minus 16 meters per second squared. All right, so t seconds after the experiment begins. Then they want the velocity function as their question. They want us to come up with v of t. Well, since we know that acceleration is the derivative of velocity, if we take the antiderivative of both sides of this, right, dt, because t is the variable here instead of x, it will back us up the chain and give us velocity. And at least these are nice power rule ones. So negative 6t, this is to the first, so I know before I took the derivative it better be squared. And technically you're still doing the over 2 thing, but sometimes people like to just look at that and say, well, I obviously need a front number of negative 3 so that when I multiply by 2 I end up with negative 6. Like sometimes they combine that into one step, totally up to you. You can always write t squared over 2 and then deal with it after, or you can picture 2 times negative 3 gives me negative 6 and then subtract 1 off the exponent. So whatever makes more sense to you, write more steps or do it in your head. dealer's choice. The antiderivative of negative 16 is negative 16t to the first. And then we might, right, always have a constant hanging out there. We don't know what it is. And then notice here's the reason they told us the initial velocity. In this case, since we know where it started, right, initial velocity means at time t equals 0, the velocity was supposed to be 45. Let's see if I plug 0 in here. Right, like both of these terms go away. And so that tells me that c had to be 0. It's like my starting point. Be a little careful, like in this one, it makes both of them go away. Sometimes if 0 is in an exponent, you still have a 1 there. So don't forget to actually visualize like what happens if I plug it in. So they told us this point so that we could figure out our starting point, basically, or figure out what our constant actually is. So instead of having a general velocity function, basically we know the shape of it. Now we actually know where it lies in the plane, because instead of some mystery number plus c, we figured out that c is 45.